Hello everyone. Today we are excited to present Project Echo Mic 1, sponsored by SANCTUARI. In this presentation, we will showcase the innovative features of our post-release tracking device specifically designed for small mammalian species. Join us as we explore the successful outcomes and key highlights of this exciting project. Our technical directors on this project are Joe Moreira, the dedicated founder and board chair of SANCTUARI, and Chris Rothwell, an ELE graduate of URI and key technical consultant of the team. Our team consists of two electrical engineers, myself, Alexei Andreski, and my partner, Grace Firth. SANCTUARI is a non-profit wildlife care organization dedicated to improving wildlife survival rates by utilizing modern technology. SANCTUARI is privately supported without federal, state, or municipal funds and is unaffiliated with other Rhode Island wildlife organizations. While there are some compact and lightweight devices available on the market that operate on very high radio frequency or various GPS technologies, there is a notable absence of mass-producible devices capable of adapting and optimizing themselves for specific environments by harnessing cellular and GPS technologies. Currently, a substantial market exists for trackers designed for larger animals such as deer or elephants. Additionally, it is our belief that many companies specializing in animal tracking devices may not prioritize the potential impact of these trackers on the animals themselves. Our primary mission is to develop an unobtrusive device that seamlessly integrates with the animal, delivering long-lasting and precise results. The consumer demand for such small trackers from animal rehabilitation centers is substantial. This tracker would provide users the ability to track animals they have never been able to in the past, opening a new world of opportunities for rehabbers. This project aims to create an integrated GPS and cellular compatible IoT tracking device designed for small mammalian species. Ideally, this device should weigh approximately 5% of the animal's weight for the entire unit, ensuring it remains unobtrusive to the animals. This multifunctional tracker is envisioned to operate seamlessly in a wide range of environments, spanning urban, rural, remote, and unoccupied areas in the United States. A paramount goal is to ensure that the deployment of this tracker does not impede the animal's natural movements and ability to carry out their tasks or lead their lives without interference, thereby allowing for discrete monitoring and research in various ecosystems. As demonstrated by the images in this slide, we successfully achieved the project's anticipated best outcome by creating a functional prototype and establishing proof of concept that such a device is possible to create. This semester, our team achieved several key accomplishments: developing a timer-based device for capturing and transmitting location data, creating an interactive user interface that allows users to visually track their location data in an aesthetically pleasing manner, and analyzing and optimizing the device's overall power consumption. The device itself contains three major components. First, the baseboard, which connects to the battery and includes the necessary I/O ports for modules being attached. Second, the microcontroller, which manages and controls the entire device's operations. Finally, the GPS/LTE module, which is responsible for collecting and transmitting GPS coordinate data. Together, these components make up the whole of our device. Our device begins by capturing the exact location data of its current position. The device then processes this data and sends it through the NB-IoT network. Subsequently, the data is uploaded to a server where the users can interact with it. Finally, the device enters a timer-based sleep state before the cycle then repeats. Throughout the semester, I was tasked with the GPS development of the device, the chosen communication protocol used to communicate between the device and the endpoint server, and finally I worked with the ThingsBoard user interface to create an interactive menu and visualization of location data. Before diving into the GPS functionality of the device, it's crucial to understand the operation of the BG77 chip, which is what controls both the GPS and LTE functionalities of our device. This chip uses something called a time-shared architecture, meaning it must alternate between functionalities. One must be on while the other is off. Throughout the semester, I spent a significant amount of time addressing errors due to a lack of initial awareness of this type of architecture. So the lesson here is clear: always fully understand the architecture of a chip before trying to do anything with it. Now let's talk about how the microcontroller handles the GPS data. Initially, we receive a GPS NMEA data string, which includes a comprehensive set of data such as longitude, latitude, elevation, velocity, number of satellites, and much, much more. Since we don't need all of these details, we specifically extract only essential information like latitude and longitude. Furthermore, our server isn't expecting a degrees minutes second format like in the NMEA string, but rather a decimal degrees format, so this needs to be properly converted. Finally, we format all the essential data into a JSON file, ensuring that the server can accurately recognize and process the incoming information. Developing the communication protocol was the next critical task in this project. In the IoT field, the MQTT communication protocol is often used due to its high reliability and efficiency in facilitating communication between endpoint devices and servers. However, MQTT does bring up some challenges for our specific application. We designed a device to enter sleep states in order to save power during idle use, which means periodic disconnections between device and server. Given that MQTT depends on maintaining a continuous connection, it is not well suited for environments where frequent connect/disconnect cycles are necessary. Therefore, it was not a viable protocol for our device. A more suitable communication protocol for our application was the HTTP POST protocol. Unlike MQTT, which requires a continuous connection, HTTP POST can effectively manage connection and disconnection cycles. It operates by sending a request, in our case, a JSON file containing GPS data, and then receiving a response that indicates whether the request was successfully processed. Lastly, we want to examine how this data is being stored. Throughout this semester, we worked with a platform called Thingsboard, which specializes in IoT-related projects. This platform features built-in widgets designed for effective data visualization. One such widget is the Maps widget, which allows for a clear representation of location data on a map. As demonstrated in the pictures on this slide, we can see the engineering building at URI with its exact location data marked by a pin. To the right is a separate widget where you can view historical data points. This aids in visualizing how the animal might have moved over time, with the movements being representative of the orange line on the map. Looking ahead, there are many potential enhancements and implementations that could be added to Thingsboard to further extend the visualization of data. And now, I'd like to hand it off to Grace.
Hello. During the semester, I was tasked with testing the power consumption of our device and analyzing these tests, finding power optimizations that would increase the lifespan of our device, and researching different antenna and battery options. For testing, I used the Power Profiler Kit 2, or the PPK2, created by Nordic Semiconductor and pictured to the right. This device allows for testing of the operational power used by the device when running. The PPK2 is created specifically to measure small supplies of currents with a range of microamps to milliamps. Using the software interface, the current coming out of the tracker is being measured, then it is able to be transferred into data that can be processed to find precise measures of the power consumption. Here is an example of a completed test on the PPK2 software. As you can see, the software allows for me to control whether the PPK2 is used as a power source for this device, as well as how much voltage I need it to supply to the rack device. There's also the ability to change the sampling rate, allowing me to get more accurate results and more specific power and timing information. Some values it gives are the average current, the max current, the time, and the charge, which I will speak more about later on. For initial power testing at the beginning of the semester, I focused on the more basic codes that were operational with the device at this time. This included ping tests, HTTP postcodes, and GPS triangulation. These first initial tests allowed me to get a baseline estimate of the power consumption our final code will need to operate, and some optimizations we can make to get the final code at the lowest possible power consumption. An example of one of these optimizations would be using parsed or unparsed data when collecting and sending information. Though it is intuitive to think the larger the messages, the more power it would consume, we wanted to verify that parsing the data did not use enough extra computational power to make parsing our data not worth it. For my testing, we've had our intuition proven correct and proceeded to use parsed data from there on. For the final power testing, I was specifically looking at the operational final code, which would be implemented in our final tracker. With this round of testing, my main focuses were on the power being drawn from operating this code and figuring out the appropriate timing of the code, seeing specifically how long the wait between information transfers should be to optimize battery life. The last part of the code I looked at was the sleep state, a key part of the code and a key part to lengthening the unit's battery life. When analyzing these final tests, I used the PPK2 software and the data values given to complete later calculations in MATLAB. To break down how this was done, let's look at the image of the PPK2 software. The figure presents the data collected in two different ways, via the selected area and the window. Using the selected area, it was easy to break down what the different parts of the code, mainly the GPS initialization, the GPS burst, the sending initialization, the sending of the coordinates, and the sleep state, consumed power-wise. The breakdown of every different section's power consumption is shown here. The main value given by the software that I used in my data analysis was the charge, given in coulombs, which can be converted into milliamp hours, the necessary unit for the calculation of the battery lifespan under different circumstances. On average, the cycle without the sleep state takes about 78.2 seconds, but for simplicity and to give some headway, 80 seconds was used in all the following calculations. Since we are using a 2000 milliamp hour battery for our tracker, all calculations made were based around that. These calculations were also based around one cycle of the code running, or finding and sending the location data one time, followed by varying sleep state lengths. This will give us a strong estimate to how long the tracker will last given different signal events and how much information the user will get based on how many cycles were successfully run before the battery dies. Since we are using a set time for the cycle, it is possible to also use the average milliamp hour to be found in the previous slide in our calculations. To account for the energy consumption during the sleep state, the average current draw is multiplied by the duration of the sleep state, resulting in the total charge used during this period. The equation seen here is the final one used for the calculation shown in the next slide. Here is shown the different signal event variations that were calculated. As you can see, there is a large trade-off between the amount of information versus the tracker's lifespan, especially in the smaller sleep state breaks like 30 seconds and 10 minutes. As you go up, this trade-off becomes less and less apparent, and the lifespan seems to flatten out. From these findings, our recommended signal event variation would be every 60 minutes, as it allows for the most cycles to occur and the most information to be gained, while still lasting a long enough time for rehabbers to monitor the animals sufficiently. The battery we have decided to use in our final tracking device is an EEMB lithium polymer battery. We needed a 3.7 volt battery as it is within the operational range of voltages found by the PPK2, and wanted the longest battery life possible without the battery being too large, so we opted for 2000 milliamp hours. To optimize the size of our tracker and make it more ergonomic, I researched smaller and more compact antennas. Throughout the testing and creation of our tracker, we mainly used the antennas that came with the rack device itself, but found that we needed smaller antennas, specifically a smaller LTE antenna, in our final device. We opted to continue to use the same GPS antenna that was provided with the device, but have switched out the LTE antenna for a YF0022AA antenna instead, which it was considerably smaller with similar abilities. This allowed us to cut the length of the tracker down while still having it operate the same. We would like to thank our wonderful technical directors Joe Morera and Chris Rothwell, who have provided us with the knowledge and guidance needed to finish this project, as well as Dr. Sunak, who has done a great job with the Capstone program as a whole. Thank you for watching.